Okay, so I want to talk today, and I'm trying to cover content which is not too taxing during the mocks, but it's still, we need to get through it. I want to talk today about this issue we touched on the other lesson, about how can we tell from a Venn diagram if two events are independent. Because if two events are independent, their circles will overlap, but if the two events are affected by each other, if they are conditional events, their circles will also overlap. You can tell if two events are mutually exclusive from a Venn diagram because their circles don't overlap. But what about telling if they're independent or not? Let's start with a couple of examples from the book which illustrate the different sorts of Venn diagrams. This question here has the first sort of Venn diagram we're likely to meet, and that's where within the circles we haven't got the probability, but we've got the number of, in this case, cards. I have to tell you, these are very rare. So we're only actually going to do this one example of this sort of Venn diagram. But this does give us our first sort of glimpse in this lesson of the notation. Just let me remind you, this means both C and K, the overlap, the intersection, N to section, N. This means either, so the union, everything united, either C or K. And then the dash means not in C. Now all of these are probabilities, and we're talking about a card from a pack of 52. So we've got probabilities with a denominator of 52 in each case. Okay, so this is page 19, question 4. See if you can have a go, and this is in, for those at home, in the Stats 2 book. Page 19, question 4. Have a quick go at those. Okay, so I've done a little reminder of the notation up here. The intersection is the things that are in both, or the things that are in A and B. The union are the things that are in one or the other, either. Could be in this, could be in that. Don't really mind. And then this is not A, so it's everything not in A. So K is 4 cards in total, the 1 and the 3 added together, so that's 4 of 52. B, there were 13 out of 52, which is a quarter. C, the overlap, 1 out of 52. The union of C and K, so that's the 12 and the 1 and the 3 added together, that's 16 out of 52. Cancels down to 4 over 13. Probability of C dash. So that's the things that aren't in the C circle. So that's these 3 and those 36. So that's 39 out of 52, which is 3/4. And then not in K, but also in C. So if I shade the area that's not in K, that's there. So how does that overlap with C? Well, it's these 12. It's 12 out of 52, which simplifies down to 3 over 13. That's no different from GCSE. That sort of question, no different from GCSE. By far the more common sorts of questions that we deal with, and again, these features at GCSE are questions like 5 that we did last lesson from page 20. So let's have a look at question 7. A bit more wordy. Can we agree that we'll have H on the left and C on the right? Just makes it a bit easier. So draw a Venn diagram, that's just like the starter question, but what about those probabilities? This time, we're not putting the number of cards or the number of people in each of the sections, but the probability. These are by far the most common sorts of questions where we're not dealing with how many people in a particular section, it's what's the probability that someone will be in a particular section. This is page 20, question 7 for those at home. So, I don't know what your strategy is, whether you work inside and then out or outside and then in. I did in the starter question, I started by writing 0.5 there, then I put 0.25 there and I had to take away 0.25 0.25 from 0.5. If you started with the 0.25 in the middle, then you can work out and get it. Don't forget the 0.35 there as well. So H union C, that's everything, H or C, so it's those three probabilities added together. Not in H, well, not in H are these two probabilities. And intersecting with C, so of those two, those are the ones that are also in C. Remember that was intersection means both. And so that's 0.15. And then H union not in C. So everything that's in H, so that's 0.5. And everything that's not in C, which is all of those. So those add up to 0.85. Okay. So let's address the crux really of this lesson, which, yes, sorry, Arthur.
Wasn't that a centre point in C? The 0.25?
Yes. So this is this cropped up the other day actually, yes. That 0.25 isn't in C, but it is in H. Because we're talking about union here, it could be in H or it could be not in C. If it's in H, I'm going to count it, even if that's not in C. You see what I mean? So yeah. I mean these are confusing. Hopefully, as we do more and more of these, we'll get better at them. But yeah, let's address the crux really of this lesson, and that is this idea that let's say you've got two events. I'm calling them A and B, and you want to check if they're independent. And by independent, I mean the outcome of one doesn't affect the outcome of the other. All right? And I realise it's sometimes hard to get your head around what's meant by independent. So let me give you an example. All right? It might be, and looking out amongst you, I can probably tell who this is, that you are like me, that your underwear drawer is neatly organised. So when I open my underwear drawer, my underpants are all rolled up, ready for that, so I just take the next one the next day. You might be some sort of maniac and just have them all thrown in a drawer. And your socks might be the same, they might all be thrown in a drawer. So let's pretend, for the purpose of this, that you're one of those maniacs, all right? Surely you end up wearing some more than others, though. Anyway, right. So this is the situation where you open your drawer in the morning and you take out a pair of socks. Let's assume your socks are all put in pairs. Please tell me your socks are all put in pairs. And you take out a pair of underpants. And let's say that we're interested in the colour. All right. So let's say A is the probability you get a blue pair of socks, and B is the probability you get a blue pair of underpants. Now, if you take out a blue pair of socks, you want, and let's pretend it's dark, you're not thinking about it, you just reach in and you take out. If you take out a blue pair of socks, you're no more or less likely to take out a blue pair of underpants. All right, we're not curating our underwear for the day. We're just grabbing two. That's an example of two independent events. Okay, the probability that they're both blue, the probability of A intersection B, is just the probability that you get a blue pair of socks and the probability you get a blue pair of pants. All right? Or, if you take the pants out before the socks, that's the test for independence. In any Venn diagram, is that number there equal to the probability in A, so those two numbers added together, multiplied by the probability in B, those two numbers added together. Conditional is the situation where you don't pair your socks up. Okay? So A, and so you pull out one sock and then another sock. So this is the probability that you pick out a blue sock first, and this is the probability you pick out a blue sock second. Now obviously, unless you have an infinite number of blue socks, if you take out a blue sock first, you are less likely to take out a blue sock second. So that is conditional probability. In that situation, the probability of A intersection B is the probability of A, so let's probably take out a blue sock, multiplied by the probability of B given that A has happened. So what that notation there means is that the fact that A has happened will affect B. The fact I took out a blue pair of socks affects the probability of getting a blue pair of socks for the second one, because there are now less blue socks. And that can be written the other way around as well. Now this notation, this given that notation, we come back to. So I will mention it now. So this is the probability B happens. And B, remember, was the I get a second pair of blue socks. That's the probability that happens, given that A has already happened. So A was the probability I get a blue pair of socks for the first one. And we remember those sorts of questions from GCSE, where you take 2 sweets out of a packet, and in some questions, bizarrely, you put the sweet back before you take another one. I mean, who wants a pair of sweet from that packet? Because everyone's been touching them and putting them back in. Or this second sort of question is where you take one out, you eat it, and you take another one out. The probabilities, in that case, it was normally a tree diagram. Probabilities in the second branch is a different to probability in the first branch. But it's this that I really want to focus on, the top, spotting independence. All right, the whole conditional thing we'll perhaps come back to, but looking out for independence, let's do an example of that. So we'll do an example together, which is actually from page 18, but I'll put it up on the board. Get rid of that. Page 18. So if we ignore the second part, if we have a look at the first part of this question, can I get you very quickly, we're ignoring the second part, so there's only 2 circles, can you knock up a quick Venn diagram for this one in the same way that we did just a moment ago and in the same way that we did in the starter? So to start with, this question is just like the one we just did and just like the one we did in the starter. So we're not... If these 2 events were independent, the probability of the overlap, the probability that they both happen, would just be equal to the probability that A happens multiplied by the probability that B happens. In this case, 0.25 does not equal 0.4 times 0.3. So if they were independent, the probability of the overlap, in this case 0.25, would be the probability of A happening on its own, 0.3, multiplied by the probability of B happening on its own, 0.4. It doesn't. It doesn't. And what that means is the fact that A happens must have some effect on B, or the fact that B happens must have some effect on A. The order isn't important. The fact is that one event is in some way affecting other. So A and B are not independent.
How do you prove it's conditional?
If they're not independent, they are conditional. So page 20, 9 to 11. The difference here is you've got 3 circles, but I'm sure you're up to it. Just for those at home, the reason we've done our diagram like this is that A and B are mutually exclusive, so they can't both happen. But we're told in this question that B and C are independent, so we know that the overlap between B and C is equal to those two probabilities multiplied together. And that's how it's presented in the diagram.
B and C are independent, which means that so if you know that you both together to work out the A as well, and then use minus the overlap.
Shall we just look at the answers here? I'm sorry if you haven't finished, but with time we'll get away with this. So this is not in A and not in B. So we're saying on this diagram, which parts of the diagram are both not in A and not in B, and that's these two. Those are the only two probabilities that aren't in the A circle and aren't in the B circle, so that's why that probability is 0.1. It's those two added together. Here, not in C and in B, so the bits of B that are not in C is 0.21. So that's this area here. So that's that bit. So A union that. So it's everything in A and that sort of crescent-shaped bit there. So that's the 0.35 and the 0.2, 0.55 and the 0.21, 0.76. Few. And then this last one appears to be everything. Let's just check. A intersection C. I better change colour for this one. Have I got a different colour? I have. Right, so A intersection C is this bit here. So firstly we've got not in that bit, so that's everything apart from that bit. Everything apart from that bit. And that's union with everything that's not in B, which is everything including that 0.2. So I've shaded everything. Everything apart from the 0.2 was this one. And it's that or everything not in B, which is everything around here. So I've shaded everything in either the left-hand side of that union side or the right-hand side, so that's why it's exactly 1. We've got time for you to have a go at one more maybe, so just move on to number 10 if you have a chance. Yes? I'd like to end a lesson on a cliffhanger, so we'll return to this lesson, this question when we meet again.